have a boundary layer around all of these surfaces that you go around here, really, really thin layer. But then you have an overall boundary layer for the water column, and yes, that will change. So over the bare sediment, it might be here, and then it might be here for these organisms. Do you all see that? See what I'm talking about? Questions? Make sense? To answer your question? Okay. Yeah, so your boundary layer is not always the same thickness. It definitely depends on how fast water is flowing and on the actual structures that it's interacting with. Do you have a question with that? No?
So would that make that area above the algae less nutrient dense compared to the bare sediment because it's not?
No, compared to bare sediment, like here and here would be like the same concentration.
Okay.
It could, because remember this is really well mixed. Above here is well mixed. So this is all mixing this way and this way, but then boom, as you get here, then this is elevated. So it's elevated above the average. It's not as if it's stealing nutrients from here or anything, because this is just mixing with the rest of the water.
Oh, okay.
This is elevated compared to that. Yeah? Okay. Any more questions? Okay. So benthic canopies attenuate flow. What does attenuate mean? This is another word for the same thing I've been saying. What does attenuate mean?
Slow down.
To slow down the flow, good. And bulk exchange rates, that's just referring to the exchange between the sediments and the water above, okay? So again, we talked a little bit about this, and we made some measurements of ammonium. The white open circles are measurements through the water column without an algal canopy present, and the black ones represent the concentrations through the canopy. So here we have the height above the sediment, and here we have ammonium concentration. And like we said before, in a well-mixed water column, no matter where you measure, it's about the same, right? That value is about the same. So at around 20 centimeters, it's about 5.5. Higher up, it's almost about 5.5 micromolar. When we look, however, at through the algae, we can see outside, they kind of match up. That makes sense, you know, well-mixed area, which is what you were asking just now. So above the water column, well-mixed. However, inside, very elevated. We got even up to 9 micromolar of ammonium. And I don't know if any of you've done any reading, but 9 micromolar is unheard of. That is an extremely high concentration for nutrients, extremely high. Actually, on average, we find things like ammonium and nitrate to be things like 0.2 micromolar. Yeah, so 0.2 to 9 is incredible. And if you think about the reef, and also I'm showing you this, remember your reef is not only made up of coral, we have lots of algae in the reef. So imagine these pockets of algae that basically just have a bunch of nutrients, very high concentrations building up underneath them. What happens in storms? When you have a storm, what does the algae do? If you have rough water, sorry? It often lifts up, right? It lifts up and it travels or it breaks up. And then what do you think happens to all these nutrients underneath here? That gets dispersed and mixed in, right? So this is really important for us. So all the time we have all of these processes happening, nutrients building up underneath, and then boom, a storm, or you just pass and kick it over, or you know, I mean, some of these are loosely attached. And then you have this pulse of nutrients. And the thing is that the reef is accustomed to dealing with it. That's not an unnatural process. So it's interesting to think about how organisms adapt to dealing with low nutrients for most of the time, and then pulses of nutrients, things that they need, pulses of nutrients. Okay. What do we have here? Oh, so same thing happening. So this is nitrate instead. So within the canopy we have high nitrate, and then in the water column we have lower values. So that's just to reinforce the same point. I'm looking at the time, so I'm going to skip through a little bit. Nitrate reductase is an enzyme that algae have to help them process nitrate. So they take up nitrate and they reduce that to nitrite, and then they reduce it further in order to build other biomolecules. The point, I put this here because I wanted to tell you it's not only the water and the concentrations in the water that's being affected, but the actual organism is also affected. So what we found is that how much this enzyme is working, like the enzyme activity, is also affected by water flow. So I did some measurements at the tip here compared to the bottom. Let's make a guess. Do you think the flow is exactly the same here and here? No? Okay, which one would be faster? Sorry? Yeah, the tip's going to be a little bit faster, right? Which means in those areas, the algae is able to take up nutrients a little bit faster, and it also means that the enzyme activity is going to be faster at the tips. So even within your organisms, you have responses to this flow. So higher flow areas, we have higher enzyme activity, and at the bottom, we also have lower enzyme activity. So it's not just the algae affecting the water, but this water pattern that it developed is also affecting its own biology. So just to summarize lots of those concepts here. Again, just a reminder here, lots of the processes taking place in the benthic environment, and what we have is nutrient release. We have high nutrient concentrations, low pH like we said, we have nutrient build up, and then there's this exchange at the edges here. This is how the nutrients are being released, right at the edge, and this is very, very slow. This can be extremely slow, okay? So, should have done that before, so we can see it better now, right? Okay, so the last thing I want to share with you guys is another part of the work that I did. So I did some of that work on these individual canopies around Coconut Island. Have you heard of Coconut Island? Who's been out there? Okay. It's a really cool place. I did some work there. But then I was interested in how can I scale this up to something bigger? I know these small canopies are effective, but what happens on a larger scale? So I did some work at local Ohia fish pond. As you can see here, have you been to the fish pond before? Yeah, do you know what a fish pond is? Who would like to share with the class really quickly about Hawaiian fish ponds? Go ahead.
Ancient Hawaiian fish pond is basically a way they would cultivate fish. So you have the makaha, or the gates, that would allow fish in, smaller fish in. But when you put down the gates, the grates are a little bit smaller, so larger fish can't escape. So every once in a while, the Hawaiians would actually go and harvest their fish from the fish pond and then restart everything all over.
Excellent. So Hawaiian fish ponds are traditional. I hesitate to use aquaculture method, but they basically, cultivate fish in here, and they depend on the tides. So on an outgoing tide, the way they tell you on an outgoing tide, now this is brackish water, so there's river inputs, okay? So this is brackish water in here. And what comes down from the river? Nutrients. So an outgoing tide, that higher nutrient water is going to come out through the makaha, or the gates. They're like sluice gates. This is a break in the water. There's a makaha here, here. This has been fixed actually 3 years ago. So there are breaks in the wall. And on an outgoing tide, this high nutrients flow out. And the way they say is that the fish just smell the sweet water, right? They know there's food associated with that high nutrient water. And it might sound funny, but that actually is what organisms do. They do sense things like that, so they know that there's high nutrients there. And the fish are not eating the nutrients, but they know there's probably algae and other things associated with that high nutrient water. So they come towards the fish pond, they come inside with these small spaces, and then they put the gates down, they basically make these bars, and they like it in here. So they stay in here, they eat, they get nice and big and fat and happy, and then they're stuck because they can't fit through the gate to get back out. So again, on an incoming tide, again, the fish are attracted towards the makaha, and instead of being able to get out because they're big and fat, they're stuck, and actually that's where the fish are harvested because they're all collected in that area. Anyway, so this is an important place culturally and ecologically. It's a gathering place. A lot of people, traditionally, this is where things were taught to younger folks. This is where food was maintained. So this is a really critical place, and I really wanted to do some work here to learn more about it and to learn from the people that manage the fish pond. So I did some measurements with algal cover, and why do you think I would measure or assess algal cover? Why do I want to know which algae is where? Yeah.
It's the different foods the different fish would eat.
It's the different foods the different fish would eat, but think of the hydrodynamics part, the water motion part of it. Why would I want to know which ones are where?
So you can know which algae is living in which type of water motion.
Which type of flow environment. And that's because what? What are the differences in algae that could be interesting? Some of them do what? Think of the structures, morphology. Some of them,
Some of them become mats.
sorry?
Some of them become mats.
Some of them become mats. They can make mat structures. Some of them are rigid. Some of them bend with flow. What would the rigid ones do to nutrients? What would the rigid ones do to nutrients? Right, the ones that bend probably won't, right? Or at least not as much. And so by me mapping out where the rigid ones are and where the flexible canopies are, I can kind of have an estimate about where I might find high nutrient areas, okay, and what's happening to nutrient distribution in the fish pond. So that was the purpose of this. I actually did a model to look at nutrient distribution in the fish pond, and the first step was first to just map out where the algae were, because these things actually affect nutrients a lot. And then I did some, can you see that? So I used my ADVs and measured water flow. So we have incoming tide, outgoing tide, and those high yellow areas are high flow areas, and those are typically at the Makaha. So I used that to measure flow. And then I combined the information and made some assessments about it. So here's a little bit about nutrient uptake really quickly. So as water flows, what is this area here below the dash line? This is the plant surface, this is the algae surface. What's this dash line pointing out? What's this area? What's that thin layer right around? You all wrote this down? This is the boundary layer, good. So what happens is you have nutrients that are going to be dissolved in the water column. Let's imagine them as these little yellow dots. Those are your nutrients. Those are dissolved in the water column. And for the plant to take it up, they have to travel across the boundary layer to get to the surface, right? Just feel like am I blocking you? Sorry. They have to travel across this layer. What we found out is that as water flows faster, this boundary layer actually gets thinner. And that's because there's more energy that could penetrate closer to the surface, right? So this layer gets thinner. If this layer gets thinner, what does it mean for these particles that have to travel across it? Is it better or worse for them? Better, because they just have a shorter distance to travel, right? Which means that as water flow increases, the algae are able to take up nutrients faster because they can just receive nutrients faster. Okay, the nutrients have a shorter distance to travel. And so when I did the work at the fish pond, I was looking at how these algae take up nutrients, how they're responding to flow, and how that's and how they're connected, and what that means for the whole fish pond. So flux of nutrients to the organism surfaces is dependent on water velocity. As water velocity increases, nutrient flux increases. So I did a bunch of these experiments. I did them at these numbered locations. The fish pond's really big. This is my flume. And this is just an image of it from above, or a diagram of it from above. So I have a trolley motor, which is basically like an outboard boat motor. Put that on, and I could control how fast the water was flowing. I set my flume over my algae. The water is flowing past it here. And during the course of the experiment, I sampled the water to measure for nutrient concentration. And I also took samples of the tissues of the algae to see how nutrients were being incorporated into their tissues, to see who was taking it up fastest. And if we look at the different types of algae, here's the Salicornia. See how rigid and kind of pulpy it is. And it's actually brittle. This breaks easily. This is Acanthopterus piscifera, that's more flexible. I also had plankton, so I used phytoplankton. Do you think phytoplankton is affected by flow? These are super tiny. Microscopic, right? Do you think it's affected by flow in the same way as the algae, larger algae would be? Guesses? It's actually not. Plankton are so tiny that these large-scale motions don't affect them in the same way. So they do not have a relationship with flow in the same way that these macroalgae do. And this is important on the reef, on the big scale, this is important. And then there's microphytobenthos, which is similar to plankton, lots of them are the same species, but these are attached to the bottom. And these again are microscopic. So if they're attached to the bottom, what's their flow environment like?
Near zero.
Near zero. Flow is extremely slow down here. So let's make a guess. Comparing the microphytobenthos to the macroalgae, which ones do you think will have higher nutrient uptake rates? Say again? The macroalgae, is that what I heard? Yes, that's right. The macroalgae have higher uptake rates because they just exist in a higher flow environment. So delivery of nutrients to their surfaces is faster. So before I continue, let's guess some more, or not guess, let's make some educated guesses. If I have, what is happening? If I have the entire fish pond covered by microphytobenthos compared to the entire fish pond covered by macroalgae, what's going to happen to the nutrients in the water column in general? What's going to be the difference? If everything was only microphytobenthos, and this takes up nutrients slower than these, what's going to happen to the nutrients in the water column?
Concentration will go up.
Say it again?
There's going to be more nutrients in the column
For which situation?
for the
This one?
macro.
Right, because it's not going to remove as much nutrients from the water column. And again, for the reef, that's important because what we're left with is higher nutrients in the water column being exited onto the nearby reef through the macaha. And so that's why I mentioned this project. So here we have MPB all the way down here. So as velocity increases, this has just a small increase in flow and nutrient uptake. But look at Acanthophora and Gracilaria, much higher than MPB, these uptake rates, right? So let's put it all together since it is time to end class. So nitrate uptake rates for all of these three benthic components were impacted by flow. So as flow increases, nitrate uptake increased. The benthic canopies attenuate flow. That one we know we could have up to 97% reduction in flow rates, water flow rates. Benthic algal canopies create biogeochemical microhabitats. I didn't use that word earlier with you guys, but these pockets of high nutrients could be considered a microhabitat. The algae themselves respond to the flow, so they have a physiological response, and I showed you that by using nitrate reductase enzyme as an example. We said this, nitrate uptake rates for all of the three components were impacted by water flow. And Gracilaria salicornia actually happens to be a major driver of nitrate drawdown because it's a macroalgae, because it sticks up into the water column, and actually also because it has a huge biomass. There's a lot of it. So it's able to impact nutrients in the water column very heavily. And that's it. So just in summary, all of these things are important. So even though we didn't talk exactly about coral today alone, the algae that live on the reefs can have a huge impact on the coral reef systems by way of affecting the nutrients, by way of covering the sediment synthesis and affecting the surface areas occupied by all the fish.
Thank you so much.